Chat with you again.
Hey, how you doing?
I'm good. I'm good. I'm excited. We're going to be talking about threading, multi-threading today. Yeah.
Multi-threading. We're basically gonna build a thread in user space, right? So we're gonna build our own threads from scratch.
Okay. Cool. I'm excited. I think I'm going to learn a lot. And if we have some folks joining us, if you like this chat or any and are interested in continuing the chat or learning anything else about distributed systems, I'm going to drop our community Discord into the chat now so that you can follow along, come bug all of the people at Resonate with your questions. Not just about Resonate. Really, I think we're pretty open to discussing all things distributed systems and application development.
Today, we're not even talking distributed systems. Today, we're talking concurrent systems. But because every distributed system is basically by definition a concurrent system, a lot of authors actually use the terminology interchangeably. It's not entirely correct, but a lot of authors use it interchangeably.
And I think it'd be worth calling out then too the distinct difference between concurrent and parallel.
Oh, that's a good one. Yeah, that's a good one, and that is literally a multi-layered one.
Okay.
So, um, all right, let's talk about that. So,
Because I have a link to your blog post here, which I'll also drop in the chat about this topic, but it'd be good to get a quick refresher.
this blog post. I do. Oh, yeah, yeah. Hold on. Gonna share my screen.
Because we can have right you're in this case in this topic today we're talking about concurrency, and this can occur on a single node, like a single application node within a single process.
Oh yeah, I do like almost a year old now. Yeah, I do like this blog post. I mean, especially look at the title picture. Yeah, it's the King Gleok from Tears of the Kingdom. Have you played yet?
I have not played Tears of the Kingdom. I've done Breath of the Wild and was blown away. I loved it. I finally got into it this last year, and yeah, I grew up on the Ocarina of Time in Nintendo 64, which
Oh yeah,
was
yeah, yeah.
the thing back in the day. I love that. And Breath of the Wild, in my opinion, like it met that and maybe even and obviously like took another step forward. But I haven't played Tears of the Kingdom, so don't
Okay,
I
I
don't.
think you're gonna like Tears of the Kingdom. It's fantastic. It hits home again, yeah, because it has the same feel as Breath of the Wild, but it like takes it up a notch. Yeah.
Ooh,
So it's like I'm sure you're gonna enjoy it. Yeah. I'm sure you're gonna enjoy it. Anyways, so let's talk about concurrent and parallel real
okay.
quick. And we start with concurrency. So now the question is, what is concurrency, right? When are two events concurrent, which could be translated to independent, right? And for that, we in order to like reason about that, we use happens before relationship as defined by Leslie Lamport. So, and the system model is actually like super straightforward. Yeah? So we have processes or locality. But let's say processes. So we have processes, and then um, we have events, and an event happens at a process, right? So let's duplicate that right away. So this is process one. It's process two. And then here we have events. Let's call this one E1.1. And then E1.2. No, 2.1. So, mm, So when are two events concurrent? It's actually a fairly simple, or when does one event happen before another event? When does an event happen before another event? And that's actually a really, really simple definition. So we have this event here is like an any event, right? So it's like whatever, epsilon, whatever happens there, right? So it's like further unspecified. So an event E1 happens before an, or E1.1 happens before an event E1.2. Yeah? If the two events happen on the same process, so here they both happen on P1 on the same process, and E1.1 literally happens before, comes before E1.2, right? So now this event happens before that event. Duh, that's the easiest definition, right? There's like, okay, sure. Now, there is one more to this, and that is if one event, here 1.3 is a send event, okay, and the other event here, E2.2, is a receive event that corresponds to that send event, then we say that this event happens before that event. This is the first and only relationship between two processes, right? So here, between these two processes. And then we do a transitive relationship, right? We say that if E1 happens before E2 and E2 happens before E3, then E1 happens before E3 done. So that's simple enough. So then here, it's like simple check. Does E1 happen before E2?
E2.2 or E2.1?
I'm sorry, E1.1 happened before E1.2.
Yes.
Exactly, yes. Yeah. E1.2 before E1.3?
Correct. Yes.
E1.3 before E2.2?
Yes.
E2.1 before E2.2?
Yes.
Yes. E2.1 before E1.2?
Well, if I'm looking at this diagram, I would say yes, but
no.
How would I be sure?
Exactly.
Right?
Exactly. There is no relationship in a happens before in the terms of happens before between E2.1 and 1.2. So neither E2.1 happens before E1.2, nor does E1.2 happen before E2.1. Now these events are concurrent. Now they are concurrent, right? So that's a very, very definition of concurrency. So now this is all in terms of events and stuff, right? So generally we think of processes. So let's do something different here. We get rid of these. We get rid of these. We don't take no. And we now define like a step, an action, an operation, and choose your poison. Yeah. And we define any operation in terms of two associated events, right? So it's like the start event and the end event, easy, right? So now we already expanded our definition to actions, right? Okay.
All right.
Are these two actions concurrent?
Yes.
Absolutely. They're absolutely concurrent. Their events are not related, right? None of the events is a send event. There's a begin event, end event, begin event, end event. And they happen on two different processes. Well, so fine. So now, since they are concurrent, the idea is that this operation, let's call it O1, and this operation O2, in terms of physical time, O1 can happen before O2, or O2 can happen before O1, right? So the scheduler is free to decide what to execute first because there is no dependency between them. They are concurrent. However, they are not parallel. They don't run in parallel, right? Because concurrency is a statement about logical time, because happens before relationship is logical timestamps, right? So concurrency is a relationship in terms of logical time. Parallelism is a relationship in terms of physical time.
Okay.
So now they happen in parallel because they overlap. If you want to be like super precise, you can say what part of them happens in parallel. But in general, if they overlap in any shape or form on a physical time, yeah, wall clock time, we generally say they're parallel, right? So now they're parallel.
And can something be parallel and concurrent simultaneously, or is it
you have to be concurrent to be even possible to be parallel?
Okay.
Yes, absolutely. Can something be not concurrent, so sequential and parallel? No, because then that would mean that the end event of one must happen before the begin event of the other. Therefore, there is a hard limit as to what the scheduler can do. Right? That would be, for example, in an await scenario, when we await something, right? So it cannot be, we're forcing synchronization, so it cannot be parallel. All right, there's something super interesting though. We can define this here as operation, right? We define this as an operation. Let's do something else, and let's define this now. Two operations, right? And we say like a process or an execution is made up of multiple operations. So here we add yet another level. We call these an execution, right? Function execution. This could be a function execution. This is a step in the function execution. Right? And then here, this one consists only of one step. That's fine. Why not? So now something super interesting happens. The executions are parallel because they overlap. Right? The executions are parallel. However, the individual steps of the execution are not, right? Because they do not overlap. So now, depending on the level of abstraction, the system is either executing in parallel or the system is actually executing in sequence. So, and that is one of the fundamental like ideas of threading, right? So you have two threads. If you only have one core, right, your machine can only do one thing at a time. Mm-hmm. Therefore, it cannot run both threads in parallel. It has or instructions of both threads in parallel. It has to run one instruction or one step or one statement, whatever we call these atomic units, of thread 1 first, then thread 2, then thread 1, then thread 2. So while on a thread level, both of the threads exist at the same time, and both of the threads are runnable at the same time. Therefore, we say the threads run in parallel. If I have only one node, one core, the individual steps of the thread run in sequence. So that's what we see here. Only if we have multiple cores could the individual steps of the threads actually run in parallel as well, right? On one core, on the other core. So that's the whole idea of the concurrency and parallelism. So, and I lay this out a little more here with like a system model and how we go through it over time, and some bonus content like blocking and non-blocking and stuff like that.
Awesome. So today, then, we're going to be working at the application level. So we're going to be doing it like coding in multi-threading, and we're doing it in Python. So we're going to be effectively creating multi-threading on a which would map to a single core like environment, right?
Exactly.
Okay, awesome,
Exactly. This is exactly what we're going to do.
excellent.
So there are different approaches to concurrency, how to manage concurrency, right? At Resonate, we do async await, distributed async await, async await. And async await like makes concurrency a first-class citizen. So there is an async call graph. It basically describes the dependencies between the concurrent units in your application. Very elegant. Yeah. Threads, my personal opinion, yeah, and the opinion shared by many people smarter than me, are not necessarily that elegant. So, or not that it's a good idea, but wild. No? So here's a really good paper. I highly recommend. The Problem with Threads, by Edward A. Lee. It's a 2006 paper. And he made the statement that we were hoping, right, we could keep the sequential programming model and just throw threads on it, and it would just be a minor addition, right? And then we have concurrency. But turns out it's a major disruption. So it's not minor addition. It changes everything. It's a very cool paper because he introduces a formal model, very high level formal model, which admittedly is a bit hard to interpret. So I had to read that paper a few times, and I may have uploaded it to ChatGPT and to explain this model to me. But it is fun. It's a fun exercise to basically like dive into his mental model and his worldview. It's a very elegant, very very minimalistic mental model. And the cool thing is basically like his conclusion. Yeah. And his conclusion is that threads are just so bad, yeah, that you just can't reason about the resulting system. It's basically, it turns something that was sequential and deterministic into something that's now concurrent and completely non-deterministic. And at the end of the day, you basically don't know what's going to happen. Yeah? So we conclude that with threads, there is no useful theory of equivalence. Yeah? So equivalent to something correct. Yeah? So very, very fun to read it. If you have some time on a weekend. Yeah? So then
Yeah.
this is a cool weekend read, no question. It's not super easy to like go through it like through and through, but totally worth the effort. So I had a lot of fun.
Curious, and no, you don't have to spoil it, but does he happen to dive into anything around what another trajectory might have been other than introducing threads? Or just
Actually, I don't remember that part. More aggressive pruning. Yes, there is definitely some stuff in there alternative to threads. I am so hung up on that, on his mental model, yeah, and his formal model, and his conclusion that I don't remember what he was talking about in the rest of the paper. It's
Okay.
like, so the fun stuff is up to page 6 for me. Yeah, it's just like not saying this is not a good paper past page 6, but this is what drew my attention. And so this is an interesting conclusion here. So threads are wildly non-deterministic. And the job of the programmer is to prune away that non-determinism. Yeah? So basically, yeah, we are confronted with a wild like possibility of nonsense, and we have to try to like bring it back to something that makes sense. Yeah? But as he says, it's so clever. Yeah? As he says, but pruning a wild mass of brambles rarely yields a satisfactory hedge. Yeah, so it's very very cool. Yeah, also it's like in a nerdy way pretty sassy. Yeah, so super cool. Yeah, it's a highly recommended paper. It's a lot of fun. But so he also mentioned that we develop tools to assist in the pruning, right? We need to basically bring order to the chaos. So coordination, it's always about coordination, right? Concurrency adds non-deterministic partial order. Partial order means this can happen before that, right? Or non-deterministic execution order. Our mitigation for that is always coordination, right? So we'll also implement one coordination tool, and that's a mutex, right? And we talk about what a mutex is when we implement it. But so we're also gonna implement mutex, right? So, but let's first implement. Let's start with the fun part, with the live coding part. No more papers. And what we gonna do here? We gonna do, yeah. So
All right, let's get into it then.
let's get into it. Okay, cool. We are set up. I don't think we have any dependencies here. Okay, threads, right? So the whole idea is you have multiple threads. Otherwise, you don't even need to do it, right? So and the idea is that something in the system executing your threads interleaves the threads. So we need something like a scheduler, right? So it's like let's implement a scheduler. Super simple scheduler, yeah? This is like thread scheduling. Super complex, right? It's a huge piece of any operating system, right? So there is a lot of smarts in thread scheduling. Not here, okay? So in our little example, there's not going to be a lot of smarts, yeah? So it's like we're just going to have an area of threads, yeah? So and we're gonna have
to make sure take advantage of gaps in execution steps and fill them in.
We're not there yet, though. We're not there yet. We will get we will get there. What am I doing? Thread. So let's have a very like synchronous interface, as ridiculous as that sounds. So structure concurrency. At first, we add a bunch of threads, and then we gonna call run, right? And then we run the threads. So what we're gonna do while we still have threads, no. So we say for thread in threads. Say if not thread done, then we say all right, thread. Okay, that's good. What is that? I don't know what that is. All right. Okay. Good.
Awesome.
So that should do it. So basically, we're while we still have threads, in the thread array, we run through the threads. Right? We take one step. We'll get to what that means, but we instruct the scheduler to take one step. And if the thread is not done yet, right? But if it's done, we remove it from the array, and we basically just make our way through the entire array, right? That's our scheduler. Again, it's not a very smart scheduler. Well, we don't need smart scheduler, right? So it's like that's cool. So now we can. I don't know why I did this. Boom. So now let's implement a thread, and here this is we're gonna take a little shortcut. We say function argument. Oh wow. Okay.
Shut up, Copilot.
That is not bad. It's not bad. All right, so we're taking a function, right? and then when we run the thread, we run the function. But obviously, right? So it's like a function runs to completion, right? Jump. Yeah. There is, and an operating system scheduler has a chance of interrupting the thread, basically from the outside, right?
Okay.
So, which is called preemptive. Since we don't want to use threads, because the point is we want to build threads ourselves, and we can actually not preempt, or at least I don't know how. We cannot preempt. I think we could mess with the debugger, but let's not go there. So since we cannot preempt a thread, we have to use cooperative measurement, coroutines, right? So we will basically yield control back to the scheduler. So that's where we fake the direction, right? Usually the scheduler is able to basically take control from you, but in our case, we will return control to you, right? So because again, we're trying to implement the threads. All right. So and then okay, what we want to do? We want to then instantiate a scheduler. Right, on the scheduler, we add and then let's add some stuff from the scheduler. What are we gonna do? We add okay, so let's define a function foo, clever, I, and then so we just do 2 steps here. No? Okay, so now we have step 1, step 2, and
I feel like I'm going to see yield statements in front of those at some point.
Soon we're gonna see some it's that's a lot. Let's do this, and I don't think that's right. Yeah, maybe it's right. Okay, we'll figure that out. And so we add 5 of those. Let's see what happens. Okay. Step 1, 0. Step 2, 0. Step 1, 1, 1, 2, 2. Right? They're never interleaved.
Right.
They're never interleaved here. So that's basically the whole point, right? They're never interleaved. So because we didn't implement threading, right? So we basically just took a function and then ran the function to completion, right? We did that on a scheduler, but we could also have called it right there and then, right? So it's like not that clever. All right, let's make this multi-threading. Now, I tweeted a while ago that you can actually do this programmatically. So what we're doing now is we basically, after each and every statement, we add a yield statement, therefore simulating the fact that the scheduler takes control from us. But it doesn't, we give it control. But you can do that programmatically in Python. Python is really a fantastic language, especially when it comes to metaprogramming. So you can use the AST, the abstract syntax tree module, read the code of this function, add yield statements after each and every statement, including nested statement like while loops and if then else, and then replace this function with the new function. So we could even do that, right? But that's kind of like a whole different episode. Yeah, and also a little bit beyond the point, because now we are more in the land of metaprogramming and syntax manipulation. So we do it just manually, right? So we say yield. Okay, cool. Then what we're gonna do? Actually, we don't have to change that much. So now foo is not just a function. Foo is a coroutine. Or generator in Python. Arguably, the correct way is to say generator. So now, let's do this differently. We take the function and therefore instantiating the coroutine. Not running it, just instantiating. So coro is now a generator, right? So coro is ready to take a step, so to say. Yeah. So how are we going to do that? Not like this anymore, yeah, but not much more complicated. So then is like correct, okay, correct, noise. All right, we're already done. So now Python itself, generators, the generator interface already has a notion, take the next step, right? That's exactly what we're doing here. Take the next step. Awesome. So that was easy enough. So see how nice and organized this is.
Yep.
Right? So yeah, that all basically goes away. Right?
Ooh, nice.
Still looks nice and organized because we basically go through the list one by one, but it's not organized in the way we want it to be organized, right? Because it's like step 1 of 0, step 1 of 1, step 1 of 2. Yeah? So either you argue it's still neatly organized, or you argue this is maximum chaos. Yeah? So it depends a little bit on your viewpoint. If we wanted to like elicit that like reaction of chaos, we could also instantiate a random number generator and then pull the here in the scheduler, instead of just like iterating through it, pull the next one randomly. But let's not go there. This is good enough. Yeah. So it's like maximum chaos. All right. What are we gonna do? We still want step 1 and step 2 to never be interrupted. Yeah? So how are we gonna do that? Coordination.
Right.
Any idea from your time of operating systems 101 threads?
Well, you said, repeat what you said before about not being interrupted. Sorry, so remind me of the goal here. What,
So
right now
we want this to always print, like we want, even though we are executing in a multi-threaded environment, we want these two to always stick together, never be interleaved. Now, since they don't do anything else, you can argue, why are you running it multi-threaded, which is a good question. Yeah. But in our case, it's a little bit beyond the point. So now we have a bunch of threads, but we want to make sure that no thread interrupts the other thread in this, what we now call a critical section.
So we want all the step 1s to execute sequentially?
No, we want it
what's
like this.
happening now.
Step 1, step 2. This is what happened beforehand.
Yeah.
This is what's happening now.
And we wanna
This
go
is
back.
our maximum chaos. We want to basically go back to this.
Got it. Interesting.
Right, so we have a scheduler, we have a thread, and we just need another construct.
Okay.
We need another construct, and that construct is a mutex, short for mutual exclusion, if I'm not mistaken.
Okay.
I want to say it's short for mutual exclusion. Actually, I've never looked that up. I'd be surprised if it wasn't. So we're gonna call it lock. No, lock is not good. We call it locked. So a mutex has two states. It's either locked or it's not locked. Or let's start with not locked, therefore it's available, or it's locked. The idea with the mutex is that only one thread at a time can acquire the mutex. Therefore, if I acquire the mutex, right, I have the mutex, that means I entered the critical section. All other threads cannot acquire the mutex. Right? Only one thread can acquire a mutex at one time. It's a very, very basic element of coordination. So I think it's the most fundamental. Right? So it's basically like a token. Or do you remember like Lord of the Flies? It's like, who hasn't read it in high school? Yeah. So where they have like a, what was it? A shell. Yeah. And I believe it was a shell. And only if you held the shell, it's not a shell, but only if you held the shell. I think it's a broccoli. Only if you held the shell, you were allowed to talk. That's basically what we're going to do. We implement the shell, and the thread can get the shell. Yeah. So, and mutex, at least in our case, is like incredibly easy to implement. Yeah? So it's like this time we're not going to let it the AI have all the fun. Yeah? We do it ourselves. So we want to acquire the AI is totally giving it away. We want to acquire the mutex, right? A thread shall get the mutex. So what are we going to do? We loop around it, right? If the mutex is locked, meaning some other thread has it, right? We don't even need to know which thread, doesn't matter.
Okay.
If the mutex is locked, we can't do anything about it, right? Therefore, we loop. We could also implement it so that it returns, but returns false, or it throws an exception. None of that. We just sit there and wait forever. Is that the smartest way? No. Yeah. Just like, does it get the point across? Absolutely. So, while that thing is locked, pass. Okay, completely wrong. While that thing is locked, we yield. Yeah. So we basically go back out, right? And then if the thread calls, or any thread calls acquire again on that thing, yeah, then we go back out, unless locked is false, yeah? And then we just set lock to true. Cool. Now the mutex is locked, right? Well, obviously, yes, what will be acquired has to be released. AI gave it away again, so let's just roll with it. So here we're gonna just set lock to false, right? So next time somebody comes in here, right, they're not looping, they are just getting locked, setting lock to true. Okay, so now how are we going to use that? Now this is a little bit more brain bendy, yeah, but it's actually a pretty cool feature. So in this episode and last episode, we used Python generators, but we used it only on, like, let's say, one level. Yeah, we yield it, and therefore, so you have a caller and a callee. The callee is the generator, and you call into the callee via next, right? And the callee yields back. Now Python can actually do that multiple levels down. So it's like, I can have a caller, a callee, another callee, another callee, yeah? And then that callee at the very end can yield all the way back out. So jumping multiple levels all the way back out. And then when I say next, I'm jumping all the way back in. It's really cool, can get really tricky, all right? But it's really cool. So that has a special syntax that is called yield from, right? Because we're not yielding, yeah? We're not yielding from here, we're yielding from somewhere else. So we say yield from, mutex acquire. That means, well, actually, let me finish up here, and then we'll talk about what that means. And obviously we need a mutex here that we share, because if everybody waits on their own mutex, that's kind of, maybe not stupid, but pointless. Kind of stupid. So we have a mutex that we share, right? So everybody has a mutex here. And then here, let's look at the code of the mutex. Here we say on acquire, right? The mutex is locked, we yield. So when we call, let's say we are foo1, right? So foo0 holds the mutex, meaning the mutex is just locked. The mutex says locked. Yeah? Now, foo1, right? We come in here, we say yield from, meaning we're just jumping in here. It's like, well, the mutex is locked, right? So then I say yield, meaning from here we jump all the way out to the scheduler. Whee, right? We completely like circumvent that all the way out to the scheduler. When the scheduler comes back around, calling next on foo1, right up here, scheduler, we are jumping all the way back in, all the way to here, because that's where we left from, right? So we're jumping all the way back in. We're immediately jumping back into the loop. If you're still locked, same thing. We jump all the way back down until somebody else says like release, right? Some other thread released it. And then that yield, basically this one, would then evaluate to false and jump here. Now, one thing though that we did not implement here is like we are not like tracking which thread holds a mutex, right? If you wanted to do something like only the thread that holds the mutex is allowed to release the mutex, right? Here, if I wanted to cheat the system, I could basically just say mutex.release, yeah? And then acquire it. But I mean, why? Yeah? So then it's like you shoot yourself in the foot. And again, it's a little bit beyond the point. So it's like all we want to do here is see how to implement mutex. So the cool thing is there's no relationship between threads and mutexes here or anything. Yeah, there's just one Boolean variable that's like it's either false or true. Right? And as long as it's true, and thread calls acquire, that thread will never take another step, and it is locked out. And then eventually the mutex is released by somebody. Again, not necessarily the one that holds it, but then you made a mistake. Arguably made a mistake. And maybe you have a good reason, but then it's like your code is even harder to understand. And then the next thread is able to acquire the mutex again. So now, given all of that, what we did, see if that works. So first, we didn't have multi-threading at all. Therefore, we were strictly sequential. Step 1, step 2 of 0, 0, step 1, step 2, 1, 1. Perfect. Yeah? Then we had threads. We were all over the place. Maximum chaos, right? Because we got interrupted after taking a step, even so we would like these to happen like together. But now with the mutexes, basically anything in between a mutex, mutually exclusive, right? Meaning no two threads can be in this section together. Mutually exclusive. Now we should see the same output as before. And boom! Now we see the same output as before. So what did we do? As the paper stated, right? We pruned away the non-determinism. Here it was just wild, arguably non-deterministic. Again, we have a deterministic scheduler, but if we throw in random, we see the non-determinism. So here non-deterministic, and now we basically build ourselves a hedge to prune the non-determinism. No, a hedge, scissors for a hedge. I forget what the correct term is here.
Here.
And hedge cutter. Yeah. And we pruned away the non-determinism and made sure that this all still happens deterministically, right? And now we have our steps in sequence once again. So that's how we built super simple threading on top of Python, just so that we can get a feel for the threading part.
Awesome.
Yeah, well, that's fun, right?
It's really cool. Yeah, I mean, how to go from order to chaos and back to order again.
Yeah, exactly. Yeah, perfect. And that's actually what historically happened. Okay, so we okay, it's gonna be an oversimplification now because I'm not a historian, but we can basically argue like the from the 50s, yeah, late 50s, all the way to the 80s was the era of, we can either say simplicity or sequentiality. Yeah. So it's like machines mostly had one core, right? You were lucky if you even had a machine. So it's like machines mostly had one core. They were able to do one thing at a time, right? And that gave rise to the quintessential programming model, the sequential programming model, step one, step two, step three, step four. Right? So then the 80s to the 80s, 90s, 80s and 90s, they were, you can argue, the era of rising complexity. Yeah? No more simplicity, but rising complexity. Because now a lot of machines had more than one core. You still had one machine. It was very likely that your stuff ran on one machine, but had more than one core. Meaning that your machine was actually able to do stuff in parallel, right?
Mhm.
Meaning it added concurrency to the table, and now you had to deal with it. So the idea here was, oh, we take the sequential programming model, right, and just throw threads on it, right? Just write your function like you always write your function and throw threads on it. Right? It's just like, again, it wasn't a minor addition, like functions plus threads, right? It was a huge disruption. So, and why? Because we didn't make concurrency a first-class citizen, right? So it's like, it was basically an afterthought. Yeah? So imagine if anybody was like not designing an airplane from scratch, but saying, it's like, now I want my car to fly. It's probably not gonna turn out well, right? So that's what we did here. And so then eventually we made concurrency a first-class citizen. There are multiple concurrency models. Golang, for example, follows CSP communicating sequential processes. But a very popular one is async await, right? So where concurrency is the first class citizen. And since the 2000s, now we have the era of exploding complexity, because now we don't only have multi-core machines, we have many machines, right? So now we have distributed systems. Distributed systems add partial failure. You know? So now parts of your application may experience a crash while other parts still run. And so that was the era of rising complexity. And what did we do there? Was basically the same idea. We do something like RPC, right? So it's like a remote procedure call. We just throw RPC on it. Yeah? And we once again hope it's like a minor addition, but once again it's like a major disruption, because we didn't make distribution a first-class citizen, right? And it's like RPC. Oh, RPC should kind of feel like it was a local function call, and like we can hide all of the differences. No, we couldn't. Yeah? So, and then now we make distribution a first-class citizen with something like Resonate and distributed async await, right? So now we have a programming model where concurrency and distribution is a first-class citizen.
Beautiful.
So I was a little yeah, history, yeah, simplified history.
Great example, man, and excellent distillation of history, which I don't think you can find really lying around. It takes somebody like yourself to mull through a lot of papers to summarize
It's
that.
a it's a lot of papers. It's a lot of like super fun nerdy papers. So I post a lot of the papers on Twitter.
Hmm.
And so if you want to follow along once in a while, and then I also hang out in the Resonate Discord. So if you want to chat about concurrency, distribution, any of the papers, if you have cool paper recommendations, yeah, drop into Discord and then we chat.
I'm adding the link to our Discord community, which is the best place to go if you want to get into this stuff with us, and particularly Dominic. And we'll add those links to any other comment sections that might not be showcasing our chat history here after the fact. We'll add those in there. Or you can go to our website, resonatehq.io. All the links are there as well. That was fun. Nice. That was actually a lot simpler, if I dare say so, than I thought it was going to be.
Right?
And um, I mean, obviously, I can see how it can get a lot more complex as soon as you say, like, for example, if any of those functions were to then sleep for a little while and you wanted to take advantage of that sleep to then execute some of the other functions, right? Because that's, I think, part of the purpose of introducing threading to begin with was taking advantage in lulls in um, function executions, right? Or you know, you have gaps or time periods of time where you have free resources available to then make use of those resources. And I can see how that would immediately become a lot more complex, but the basic of it, like, was much more simple than I was expecting, to be honest.
Yeah, the basic idea, the essence of it, right? Of course,
Yeah,
once you want to transform that into a full-fledged production system threading, that also takes periphery into account that is in itself asynchronous, right? Then it's, of course, it gets much more complex really, really quick. But the essence, I love that you can play with how much is it? It's like 62 lines. And you can explore like the essence of a problem, and you can throw deterministic simulation testing on it now if you want. You can then pseudo randomly run through the steps and check the different interleavings. So it's a lot of fun if you write something minimally. Right? It's a lot of fun if you write something minimally and then start exploring its behavior. It really helps to distill the essence of concepts like for a mental model.
totally.
And you know what we can do one of the next live streams. So I tweeted a lot this week about event driven systems, and I made the statement that events are the wrong abstraction for event driven systems, which may sound like a contradiction in and of itself.
Hmm.
But before we even go there and resolve that contradiction, what I was a bit frustrated, or I'm still, what I'm a bit frustrated about is that there is no formalization of what is even an event-driven system. What is it, right? It boils down to the point that there is no formalization of what is an event. What even is an event, right?
I've always been
And
frustrated by that as well. Yeah.
right, super frustrating feeling, yeah. And it's like I did a lot of looking around for papers. If anybody has a paper in mind that formalizes the notion of event driven, I'd be very happy to read it. But I looked around a lot, I didn't find anything. So I started to build my own formalization, a minimal model of what is event driven, to really understand the very, very essence, yeah, of event driven systems and start to reason about them. Where is it? Where is it appropriate? Where is it like, where does it provide delightful developer experience? Where does it provide a dreadful developer experience, right? Based on these terms. And what higher level abstractions do we have available that we can put on top of event driven systems to make them more delightful to develop? So we can look at that at the next live stream. It's more theoretical. It's less coding. It's gonna be one or two formulas, but super simple formulas.
Well, I'm looking forward to that because I find it difficult to draw the line between what is not an event-driven system and what is.
Yeah,
You know,
yeah, exactly.
yeah. So that would be great. That would be awesome. And I sure hope anybody following along that is interested in that will join us.
Awesome. Let's do that. Live
Cool.
streaming. What is an event-driven system? The very essence of it.
Yeah, we'll schedule that for next week. Next Friday, same time, same place. Does that sound good?
That sounds good.
Cool. Well, this is awesome. Perfect. I think we're ending. Got just a few minutes left here on our schedule, but I think that pretty well wraps it up for us. And if we've got, I'll connect with you after this, and maybe we can get that code up into a public repository for people to check out, and we'll attach it to our recordings under the comments.
Yeah, no problem. That's basically just a GitHub gist. Yeah. Maybe I just ask ChatGPT to write some comments for it, and off we go.
Perfect. Perfect. Amen. Thank you, GitHub Copilot, as well, for your help in
Oh,
this.
that's right. That's right. Cool.
Cool, man. Thanks, Dominic. Appreciate it as always. I'm a huge
I
fan.
thank you.
Cool. And thank you for everybody following along, and we'll hopefully see you next week.
Awesome. Thank you very much, everybody. See you later. Bye bye.